Oh.
Yeah. Just the text box is what he said at the time. And now he's going to tell us.
That's all. You can leave around. Okay. Good morning. Morning. Guess not that good for you. This is a good morning. It's first day of the week, so there's a lot of things going on in the School of Engineering this week. I don't know if you're aware, we have the AVIT accreditation going on right now for the IE program. So if you see a group of people, it look like faculty members walking around the hallways, it's because they're doing the evaluation specifically for the IE program. Okay, we have a couple of students attending to some of the activities today. So if you see one or two students leaving the classroom early, it's because they're going to be attending to one of those meetings. So in terms of the course, we have, I'll say, around 4 more lectures for our third exam. So the third exam is going to be the last day of the semester, the last day we have 4 lectures. So again, as a reminder for you, if you do well on the third exam and if you're satisfied with your grade at that point, when you take into account the exams and the homeworks, then you are not forced to take the final. So it's going to be your decision at that point if you want to keep your grade as it is with the 3 exams and the homework. I'm going to notify you what will be your grade at that point. So I'm going to do this by email. By email, you're going to respond to me if you want to take the final or not. Okay. Remember, if you decide not to take the final, the percentages for the grades are going to be different. So you can refer to the syllabus for that. You can see that if you take the final can help you improve your grade. Okay, so that's an option that you have if you like to take advantage of that. In terms of any questions? Yes. Yes. Again, that was a question that was asked at the beginning of the semester. When you go take the final, you should be prepared. So I don't want you to go take the final and not be prepared. So I will expect you to do better. I mean, the final should be an opportunity to improve your grade. I cannot guarantee that you will do better. So that's why you have to make a decision whether you think that you feel comfortable to do the final option and do well. The final is going to be comprehensive. In my experience so far at Texas State University is that the student who takes the final usually do well and improve their grades. Okay? But right now 100% of the students have done better and have improved their grades, but I'm not going to say that you are guaranteed to do better on the final. Okay? So I don't know if that answered the question or not. Any other question? Okay, so in terms of the material, we started covering sampling distributions and talking about the distributions, the probability distribution for some of the probability parameters, specifically for the mean and the variance. And the last thing we did was to discuss the sampling distribution for the variance. And we were talking about the distribution of t, which is similar to the distribution of z, which is the standard normal, which is symmetric with the bell shape. So we discussed a couple of examples for the t distribution, and we also talk about how to use the table to get those probabilities. So if you don't have a copy of the table, I have extra copies here, so I can distribute to you if you still don't have a copy of that table. So we discussed this problem, and we're computing. Actually, the first part was just to see if you can get the number from the table, or that probability, and the value of t from the table. And then we cover how to compute the probability for that specific problem. I have another example here. In this example, again, it's just to get you familiarized with the table for the t distribution. And in here, what I want you to do is to find k. K is the lower bound for this range. And basically what we're saying is, I want you to find k, so this range will give you a probability equal to 0.045. So this problem is very similar to the problem we discussed on Wednesday last week. And we have extra information here for a random sample of size 15 selected from a normal distribution. And we have the parameter here to compute t random variable. Okay, so again, what we are trying to find here is just that value of k, in which we're going to be able to get that probability of 0.045. So if you look at the graph here, we have the shape, or the bell shape for the t distribution. We have the upper bound right here, t minus t 0.005. If you look at the table, the value for the probability that gives you this t value is 0.005. So if you go to your t distribution table and you find 0.05 with 14 degrees of freedom, that value should be equal to minus 1.761. That should be 0.05, right? Minus 1.61. So let me write that down. So t of 0.05 with b equals 14 is equal to 1.761. But what happened? Here we have a negative value. So last time we learned that, therefore, negative t 0.05 will be equal to minus 1.761. So negative t will give you that negative number for the probability. So based on this, k should be a negative value, or t of alpha should be a negative value, because that upper bound of the probability is a negative value, and our t value is a negative value. And we know that our upper bound will be to the right, so if that is a negative value, any number to the left will be also a negative value. So k will be a negative t because is to the left of minus t 0.05. So this should be minus t of 0.05. Okay, so then we have 0.05 minus alpha should be equal to 0.045. So if you look at that area, it's 0.05. And you know this area is 0.45. Then the difference between alpha, so alpha should be 0.05 minus alpha should be equal to that probability that's given. And that is based on the area of the probability. So if we solve for alpha, then we get that alpha equals 0.005. And using that information, we can find the value of t. So k will be equal to minus the value of t at 0.005 with 14 degrees of freedom. And if you find that number in the table, that's negative 2.977. Okay, so having those two numbers, now we have the value for the lower bound for our probability. So we know that the probability of t being within minus 2.977 less than t less than minus 1.761 should be equal to 0.045. Yes. Degrees of freedom are always the value of n, the size of your sample, minus 1. Okay? Good question. Okay, so this is a different way of computing the probability. You have the probability already, and you want to know what will be the size of that interval that will cover that probability. But if you think about it, this problem is solved in the same way as we solved the previous one. Now we have a more applied example. And I want you to pay attention because then you're going to have the opportunity to work on a lab on a similar problem. So here we have a chemical engineer claims that the population mean yield of a certain batch process is 500 grams per millimeter of this raw material. To check this claim, he samples 25 batches each month. If the computed t-value falls between these t with alpha 0.05 negative and positive, he's satisfied with his claim. So the question is, what conclusion should he draw from a sample that has a mean, this should be x bar, of 518 grams per millimeter and a sample standard deviation of 40 grams. And again, this is assuming that the distribution of yields is approximately normal. Okay, so by looking at the problem, we have the criteria for evaluation, which is this t-value that we are going to compute. This to be between minus t of 0.05 and positive t of 0.05. And we need to get the t-values for those probabilities, and then we're going to assess our statistic within those bounds. And if the statistic is within those bounds, then we can tell that, yeah, the claim is true. But if it is outside bounds, then we are not certain that those claims are true. Okay, so from table A4, again, this is the tables that were provided to you last time for the t distribution. From this table, A4, t of 0.05, the value for that t is 1.711. And again, we are using how many degrees of freedom? What would be the value of degrees of freedom? Correct. So degrees of freedom are always n minus 1. So we have a sample of size 25. So our degrees of freedom are 25 minus 1. That's 24. So the engineer can be satisfied with his claim if a sample of 25 yield a t-value between minus 1.711 and 1.711. So now what we need to do is to compute our t-value for that information that we have from the problem. So we know t will be equal to x bar minus mu divided by the sample standard deviation divided by the square root of n. So we know the value of x bar, that's 518. Mu is 500 grams. Standard deviation for the sample is 40. And we know this is the square root of 25. So that value is 2.25. So what can you tell about this claim? So, correct. So the claim is not valid because this number, this t value that we compute based on the information from the sample, is over this range. So it's higher than 1.711. So his claim is not valid. Okay, so again, we are looking at the variability of the samples. So we are trying to see if the variability they're claiming for their experiment is actually true based on the t distribution or t sampling distribution. So we're saying the probability of this claim be true, for that to be true, then it has to be within these values. If it is not within those values, then that claim is not valid. Okay, so now you're going to have the opportunity to work on the problem on teams of 2 or 3. So I'll give you 5 minutes to work on this problem. Make sure that you have a table. Yeah, I can provide you with the problem.
Is the person who made it?
Yeah. You guys are tracking these up here, don't you? Exactly.
That's negative 2.1.
So we have from the table we can get the value for t. T point 0.025 should be equal to 2.131, and this is with 15 degrees of freedom. Then we can compute the value of t, which is equal to x bar minus mu divided by the standard deviation of the sample divided by the square root of 10. And this is 27.5 minus 30 divided by 5 over the square root of 16 should be equal to minus 2. So minus 2 falls between minus 2.131 and 2.131. So the claim is valid. Any questions? Good. So that problem again concludes the topic on sampling distributions. We're going to transition now to a different topic. So let me just conclude here. So with this topic, we complete the fundamental sampling distributions and data. Again, we covered the sampling distribution for the mean and the variance. And we conclude, we talk about the t-distribution, the central limit theorem, and we also talk about the chi-square distribution for sampling distribution. So this is material for your third exam. Any questions? Okay, so let's transition to a different topic on this along the same lines. Okay, so now we're looking at 1 and 2 sample estimation problems. This topic is coming from, or you can read about this topic in chapter 9 of your textbook. And what we're going to do today is basically go over the first 3 topics. We're going to talk a little bit about statistical inference. We've been discussing in general what statistical inference in class, but today we're going to discuss in detail what it is. We're going to discuss the classical methods of estimation, and then go and study some single sample to estimate the mean. So you should be very familiar with the roadmap for the course. We studied statistics initially, then we transitioned to probability, and now we are kind of mixing the two with the sampling distributions and the probability distributions. So now we are considering the sample estimation. So the learning objectives is you to be able to construct confidence intervals on the mean of a normal distribution using either the normal distribution or the t-distribution method. Also, I want you to construct confidence intervals on the variance and the standard deviation, and construct confidence intervals on the population proportion. Finally, I want you to use a general method for constructing an approximate confidence interval on a parameter and construct prediction intervals for future observations. So now, instead of looking at point estimates, we're going to be looking at how do you estimate this parameter, but since we are not 100% sure that that parameter is going to be the same as the population parameter, we need to provide some confidence intervals that will tell us with some probability this estimated parameter is here. Let's say we have this is mu, this is the population mean, and now what we are doing, this is considering all the observations from your experiment. What we are doing now is we are getting some information as a sample, and we are computing some parameters. Let's say x bar 1 from the sample, but we know that x bar is not close. It's not the same as the population parameter. So what we do is let's try to estimate with some confidence how far this parameter is from the true value. So with this confidence interval, what we're going to add is some range. Doing this a little bit. So we can say, okay, so with let's say with 85% confidence, that interval is going to contain that population parameter. Now, what happened? The shorter your confidence interval is, the better your estimation. So if you're able to compute the confidence interval, let's say with 95% confidence, that will basically say with 95% confidence, that interval will contain the true population parameter. Okay, so that's a small introduction of what we're trying to do with these confidence intervals. So let's talk first about statistical inference. So statistics is concerned with making inference about the population and population characteristics. So we are taking samples and we are trying to make some inference about the population based on the sample. So statistical inference consists of those methods which one makes inference or generalizations about the population. Again, we are going to making some conclusions based on the sample, and those conclusions are basically trying to predict what's the behavior of the population. So statistical inference may be divided in two major areas: estimation and test of hypothesis. And the test of hypothesis is the last thing we're going to do in this course. With this, we treat these two areas separately. Theory and application of estimation is going to be part of this lecture, and the hypothesis testing is our last lecture for the course. So to distinguish clearly between the two areas, I'm going to show you two examples. So for estimation, let's talk a little bit about the elections. Candidate for public office may wish to estimate the true proportion of voters favoring his candidacy. The fraction of voters in the sample favoring the candidate could be used as an estimate of the true proportion in the population. Knowledge of the sampling distribution of a proportion enables one to establish the degree of accuracy of such an estimate. So based on the sample, let's say we are having we have two candidates for president, and we want to know what's the proportion of voters that will go for one or the other based on Texas. Then we do an estimation based on the sample. Now, in hypothesis testing, which is again the last topic of this course, we are interested in a different type of conclusion. So consider the case in which one is interested in finding out whether brand A of floor wax is more shock resistant than brand B. So we have a comparison of two different products. He or she might hypothesize that brand A is better than brand B, and after proper testing, accept or reject this hypothesis. So here we are not interested in computing a parameter or saying the average duration of this wax in your floor. No, we are not interested in that particular type of conclusion. What we want to know is, of the two, I'm predicting one is better than the other. And I'm going to run some hypothesis, I'm going to run some experiment and find out if one is better than the other. And I'm going to accept or reject this hypothesis. We don't attempt to estimate a parameter, but instead we try to arrive at a correct decision about a pre-stated hypothesis. Okay, so that's the major difference between two types of testing. You need more time? So now let's talk a little bit about the classical methods of estimation. So again, this lecture is focusing more on the estimation side. The last lecture of the course will focus on the hypothesis. So classical methods of estimation, a point estimate of some population parameter. So now I want you to try to understand the difference between these symbols. So when I use theta by itself, that means that represents the population parameter. See? Then if I have theta hat, that is a parameter that is coming from the sample. And we also have the statistic value. Okay, so for example, the value of x bar, small x bar, of the statistic x bar, computed from a sample size of n, is a point estimate of the parameter mu. So mu is the parameter from the population, and we are constructing, or we are sampling, or we are getting an estimate of that parameter from the sample. Similarly, p hat, again, is coming from a sample. We have small n, is a point estimate of the true proportion p from my binomial experiment. An estimator is not expected to estimate a parameter without error. So this estimator is not guaranteed to give you the right value of the parameter from the population. Again, these are estimators. So we do not expect x bar to estimate mu exactly, but we certainly hope that it's not far from it. So again, you compute the x bar from the sample, it could be here, but the true population parameter is here. So we want some estimators that are good, so they are going to be close to the true population parameters. So consider, for instance, a sample consisting of kids with age 2, 5, and 11 from a population whose mean is 4, but it's supposedly unknown. So you're doing this experiment and you don't know this value beforehand. So this value is unknown. We would like to estimate that value, and we can use different ways of two different types of estimators. For instance, you can use the sample mean as our estimate, and if you compute the sample mean, you'll get 6. You can also use the median as your estimate, and then in that case, the median could be 5. But what happened? Not knowing the true value of the population parameter, we must decide in advance whether to use X bar, which is our sample average, or our median as our estimator. But as you can see, those two values are different from the population parameters. So you need to decide whether to use one or the other, but in both cases, they are not, well, one is closer than the other, so you need to find a better way to find your estimate. So, an unbiased estimator, and I ask you a question here, what are the desirable properties of a good decision function that will influence us to choose one estimator rather than the other? Well, let this theta hat be an estimator whose value is the point estimate of some unknown population parameter. We would like the sampling distribution of these statistics to have a mean equal to the parameter estimated. An estimator possessing these properties says to be unbiased. So the type of estimator that we would like to have are those that are called unbiased estimators. They are close to the true population parameter. And I'm going to show you one of them on the next slide. So, proper definition, statistic is said to be an unbiased estimator of the parameter, of the population parameter, if that mu, or the expected value of that statistic, equals the population parameter. So what we're saying is we're coming up with estimators that when you look at the expected value of that estimator, the expected value of the estimator is going to give you the true value of the population parameter. So let me show you that with the next example. So the variance of a sample is one of those cases in which you can have an unbiased estimator. So what we're saying is when you look at the expected value, let's say you have a population, you get a sample, you compute the values of that sample. When you look at the expected value of the variance of the sample, the result that you're going to get is the population variance. So even though you're getting the information from a sample, it is an unbiased estimator and it's going to give you the population variance. Okay, and we can show you that. So by definition, we know how to compute the variance, right? So now let's look at the expected value of the variance. So you know how to compute the expected value. You're going to look at the expected value of the x, which are your random variables. So here you have two different types of random variables. You have x, and you have x bar. So we can do some math here. Basically put the expected value, separate them, and put them in this form. And after that, we know that this defines the expected value of xi minus mu squared is equal to the standard deviation of xi, of the values of xi, of the random variable. And we know that this expectation, x bar minus mu squared, is equal to the variance of x bar. So by doing some substitutions again, we know that this value, this variance of xi equals the variance of the population, because we are considering all the xi, and we know from the central limit theorem that this value equals sigma squared over n. So by doing those substitutions, we get the following expression. And when you solve this expression, this is what you get. So the unbiased estimator, the expected value of the unbiased estimator is giving you the population value. And I don't expect you to solve this and to show me this in your exam. This is high level stuff. But what I want you to understand is that we can have some estimators that will give you the population value. Okay, and those estimators are called unbiased estimators. Let me know if I can move to the next. Okay. So the values of a point estimator, let's say we have if statistic 1 and statistics 2 are two unbiased estimators of the same population parameter theta, we want to choose the estimator whose sampling distribution has the smaller values. So the one with the smaller values are the ones that you want to choose. If we consider all possible unbiased estimators of some parameter theta, the one with the smallest variance is called the most efficient estimator of theta. So you can have multiple estimators, unbiased estimators, but the one that has the smaller variance is the one that you want to select because it's the most efficient one. And to show you that with the figure, here we have three different statistics to estimate the same parameter. We have the parameter, population parameter here. This is the center. And we have three curves. One for statistic 1, statistic 2, and statistic 3. From those three statistics, there's one of them that is not an unbiased estimator. Can you tell which one it is? 1, 2, or 3? Two of them are unbiased, one of them is not unbiased. So, unbiased basically tells you that the estimator is giving you the same value as the population parameter. So these two curves, 1 and 2, are centered on that parameter. So those two estimators are unbiased. But this one, 3, is not centered on that population parameter. So that tells you right there that it's not unbiased. It has some bias, so that's why the center of the curve is not here. Okay, so 1 and 2 are unbiased, but you can also notice that the values for those estimators are different. So the figure illustrates sampling distribution of these three estimators. It is clear that only 1 and 2 are unbiased, since their distributions are centered at theta. But the estimator of the statistic 1 has smaller values than the estimator for the statistic 2. And therefore, it is more efficient. So 1 and 2 are centered on the same population parameter, but as you can see, 1 has a smaller value because statistic number 2 is more spread. Okay, so now let's talk a little bit about the interval estimation. An unbiased estimator is unlikely to estimate the population parameter exactly. Sometimes it is preferable to determine an internal or interval with which we will expect to find the value of the parameter. Such an interval is called the interval estimate. So what we are looking for is to provide, to this estimate, we're going to provide an upper bound and a lower bound. Just like I explained here, we're going to provide those bounds, and we're going to have with some probability, we're going to say, okay, with this probability, we are 95% sure that the true population parameter will be within these bounds. So an interval estimate of a population parameter, theta is an interval on the form like this. So these upper bounds and lower bounds are the value of the statistic for a particular sample and the sampling distribution of that statistic estimate. Let's look at this example. A random sample of the SAT verbal scores for students entering the freshman class might be produced an interval from 530 to 550, within which we expect to find the true average of the SAT verbal score for the freshman class. The value of the endpoints, these two endpoints, will depend on the computed sample mean, X bar, and the sampling distribution of X bar. Okay, so the values of the endpoints, one more time, will depend on the computer sample mean and the sampling distribution of that parameter. The interpretation of the interval estimates, different samples will yield different values of the statistic and different values for those lower bounds and upper bounds. So, for instance, if we have population, right, we know the parameter for mu. If you get one sample, you can have an estimate with an interval here, and then you take another sample, it's here, and then you have another sample, it's here, and then you can have another sample. So depending on how many samples you have, it should be a plot. You have 6 different estimation for your parameter, and you have also different range for or upper bounds and lower bound for each parameter. So from the sampling distribution of the statistic, we should be able to determine these lower bounds statistics and upper bound statistics such that the probability of being within, the probability of these true statistics from the population being within those statistics is 1 minus alpha. So we have a probability of 1 minus alpha of selecting a random sample that will produce an interval containing that true population parameter. The interval is again this one. These are two statistics. It's called a 100% 1 minus alpha confidence interval. The fraction 1 minus alpha is called confidence coefficient or the degree of confidence. And these are concepts that you're going to have to remember from now on, specifically if you are taking courses in which you're going to be performing experiments. Most of the outputs of your experiments are going to be reported with confidence intervals. Okay? If you perform an experiment based on a computer, you're using different scenarios. Those scenarios are adding randomness to your model. You are not, if you report a number, let's say you're running 10 different experiments and you're saying the average of the speed of this conveyor is 20 based on 10 experiments. That number is not true. Because again, based on what you're learning in this class, that output is also a random variable, and you are not considering all the scenarios, you're just considering a couple of them. So if you say, based on the number, the average is 25, but the true is 35, that number that you're reporting is incorrect. So that's why you're going to be reporting your experiment based on confidence intervals. So you're saying with 95% confidence that average should be here. Okay? So I'm just giving you a heads up from now on. So the endpoints, lower bounds and upper bounds, are called the lower and upper confidence limits. So when alpha equals 0.05, we have a 95% confidence interval. The wider the confidence interval, the more confident we can be that the interval contains the unknown parameter. Ideally, we prefer a short interval with a high degree of confidence. Okay, so what you want to do is to have a high level of confidence and at the same time have a short interval. So now that we discussed the theory and also that we discussed the purpose of these confidence intervals and these estimations, Now we can look at the math. So let's say we have a single sample and we are trying to estimate the mean. So consider the estimate of the interval estimate of mu. We can establish a confidence interval for mu by considering the sampling distribution of x bar. So again, mu is the population mean. Every time you see mu, it's the population mean. And we can establish a confidence interval for mu by considering the sampling distribution of this x bar, which is the estimator of the population mean. X bar is the sampling. It's coming from a sample. It's the sample mean. Okay? So according to the central limit theorem, the sampling distribution of x bar is approximately normally distributed with mean mu x equals mu and standard deviation equals sigma over the square root of n. So that's something that we learned. We learned the central limit theorem and we know the shape of the normal distribution. So this concept is going to allow us to define a confidence interval for the mean. So we can see for the figure that the probability of being within minus z over alpha half and z of alpha half is going to be this area. What will be this area right here in terms of alpha? That will be 1 minus alpha. And why is that? Why is this 1 minus alpha? Do you know this area? This is alpha half, right? This is alpha half. So if you subtract 1 minus alpha half and minus alpha half, then you get 1 minus alpha. So this area, that's the probability. We want to know what is the probability that this interval is equal to 1 minus alpha. So multiplying each term, and we know the value of c, so we can actually say that the probability is going to be equal to this same thing, but by substituting this number or this estimator, we can put that into here. So now we have a different expression. We can multiply each term in the inequality by the sample standard deviation, and then subtracting x bar from each term and multiplying that by minus 1, we obtain this expression. That expression right there is a confidence interval. So what we are saying is the upper bound is defined in terms of x bar, which is your estimator for the population mean, minus this term is going to give you your lower bound for mu. Now, the upper bound is the same term, but instead of subtracting this number or this value, you're going to add that value, and the probability of mu being within those intervals is equal to 1 minus alpha. So, if you let alpha be 0.05, this will become 95%. You're going to use the value of 0.05 here for your t. That's going to adapt your range within the probability distribution of the normal. So you know alpha will depend on the z values are going to depend on alpha. So the higher you have your probability, you want to cover more area, then the wider your confidence interval. And here is again the confidence interval for mu, knowing mu and sigma. This is the confidence interval for the population mean, and it's just the same expression that we derived on the previous slide. So an interpretation, theoretical interpretation of the confidence interval, clearly the values of the random variables for the lower bound and the upper bound are the confidence intervals or the confidence limits. So we can say that this statistic or estimator will be equal to that lower bound of the confidence interval, and we have this estimator for the upper bound of the confidence interval. And this is the figure that I'm being using to explain you the meaning of confidence intervals. So as you can see here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 confidence intervals. These confidence intervals are coming from these 10 different samples. So we're saying they're coming from the same experiment. Let's say you're analyzing batches of a certain product, and you're collecting different samples from these process. So the first sample you collect is X1 bar, X bar 2, X bar 3, X bar 4, 5, and so on. So this is X bar 10. So you have different estimators for your sample mean, and those are represented by double dots. 10 samples, 10 different sample means, right? Make sense? You're getting samples, different times, you get different means for each sample. Now you compute the confidence interval for each sample mean, and this is how spread those confidence intervals are. Can anyone tell me what will be the confidence of that experiment or that confidence interval by looking at the figure? That is correct. Anyone else? You have 10 confidence intervals. One of them is not including the population parameter, which is this one. So your confidence for the confidence interval, or the confidence interval that you're using for this experiment, is 90%. Because 9 out of the 10 are going to include the true population parameter. Okay, so interval 97 is not including the population parameter. So you can say your confidence interval is going to include the true population parameter with a 90% confidence. Questions? So different samples yield different values of X bar and produce different interval estimates of the parameter mu. So you have different confidence intervals for each sample. Some of them are going to include the population parameter, some of them are not going to include the population parameter. Okay? And as I stated, based on these 10 confidence interval, we can say that there's a 90% confidence on this particular one. Okay, so an example here, the average zinc concentration recovered from a sample of measurements taken in 36 different locations in a river is found to be 2.6 grams per millimeter. Want you to find the 95% and the 95% and the 99% confidence interval for the mean zinc concentration in the river. Assume that the population standard deviation is 0.3. So what do? We know the definition of the confidence interval. So we have X bar is 2.6. We have the 95% confidence first. So for 95%, alpha is going to be equal to 0.05 because it's 1 minus alpha. Okay? So we know how to compute the confidence interval. So the lower bound is this. Confidence interval for mu, and this is X bar plus Z alpha over 2 sigma over the square root of n. So Z of alpha half will be equal to Z of what? Will be alpha half. We know alpha. Alpha half is 0.025. right? Is the half of the value of alpha. So if you find that number from the normal, again, now we are using Z. Z is for the standard normal distribution. You need to use the standard normal table. And that is part of the first group of tables that I provided you. So this is 1.96. So we have all the terms that we need. We have the sample mean, we have Z, and we have these numbers. So we can compute this confidence interval. It's 2.6 minus 1.96 times 0.3 divided by the square root of 36 less than mu less than 2.6 plus 1.96 times 0.3 divided by the square root of 36. In this confidence interval equals 2.50 less than mu less than 2.7. And that's for 95%. Now you also need to compute the confidence interval for 99%. In a question that I have for you, and I always ask this question in the exams, if I ask you to compute the 95% confidence interval, and then I ask you to compute the 99% confidence interval, what would you expect to happen with this confidence interval? Do you think it's going to be larger or smaller? We're going to show what will happen. I just want you to think about it. So 95% of the time you want to include the true population parameter. Now if you increase that to 99%, let's compute what will happen. 99%, that means alpha is equal to 0.01. Z equals this. So this is Z of 0.05, and this is going to be equal to 2.575. So if we compute this, minus 2.6 minus 2.575 times 0.3 divided by the square root of 36 less than mu less than 2.6. Yeah, that's equal sign, sorry. Yes, and minus 2.556 times 0.3 divided by the square root of 36. If you compute this, this is 2.47 less than mu less than 2.73. So the confidence interval actually expands. And why is that? Because if you have a 95% confidence interval, you computed this, right? So you're saying 95% of the time, your sample means are going to be included in this confidence interval. So that makes the confidence interval a little bit smaller. But if you want to include 99%, then what will happen is you're going to expand this because you want to make sure that 99% of the time the true population is included. The higher the confidence, or the probability actually, the wider will be the, well, I don't want you to get confused. One thing is alpha and one thing is 99% probability. Yes, sir.
Which is it the normal distribution?
Yes.
How are you getting that? Now, you go to Z,
You have to go inside the table for that look for that probability. So in this case, 0.025 inside the table. Yes. Good question. Yes, sir.
What's right there? You see on the bottom, 0.6, says intensity process.
This one? Yes. That should be positive. Any questions? So I'm going to stop here today, and we're going to continue on Wednesday. There's just one more thing that we need to discuss for this chapter, well, this lecture. The lecture for Wednesday is already available on track, so make sure that you print that. And you have homework that is due on Wednesday, so make sure that you work on that homework.
She knew what she was doing. I typed it in wrong to the calculator. Is there a way that she can get the point and I don't? Because that's not fair.
Show me
It's, yeah, she. No, not that one. Yeah, see, we have it all, and I just typed it in wrong.
Okay, I was just making note.
Thank you. I appreciate it.
Could I get the slide?